Today we are going to be talking about the scientific method. I mean, biology is a science, okay? It's the scientific study of life. And scientific method is really a method of reasoning, okay? It's a formal method of reasoning that works, okay? It keeps you from repeating yourself, it keeps you from missing things and all of that. It's just a standardized method of working. It begins with observations. You see something and you wonder what's going on. Sometimes you just get information from another scientist, but by following a series of steps that includes experiments, you come up with a hypothesis trying to explain what you just observed. You see whether the hypothesis has been supported or not. If the answer is no, then you can come up with a new hypothesis. So we're going to study it slowly. Just going to mention in here, this is Francis Bacon, that was credited with being the first person to document scientific method. Basically, with scientific method, you make an observation. I just come home, click the switch, and the light does not come on. So you ask a question. Why didn't the light come on? You try to answer the question to yourself by making a hypothesis. The hypothesis needs to be tested and say, well, I think the reason the light did not come on is because the light bulb is stored. Well, a test would be to take off the light bulb that I think is bad and put a new one. If the light comes on, I know my hypothesis was right. Okay, good. So in this case, my hypothesis was supported with the experiment. But let's assume that I replaced the light bulb and the light does not come on. Well, the hypothesis is not supported. Try again. What else could be wrong? Oh, it may be the circuit. So I can go to the switch box and realize that one of the switches had tripped. Once again, if that's not the answer, you just keep on trying. But you make a hypothesis, you test it. If your experiment supports the hypothesis, great. If it doesn't, then you make another hypothesis and you keep doing it until you can explain the result. It's not that complicated. So basically, what we're doing is using what we call inductive reasoning. You use your creative thinking to combine isolated facts into a whole. Okay? You're trying to say, okay, I came in here, it's dark, I tripped the switch, the light did not come on, I know what the lamp looks like and all of that. So you come up with hypothesis, a possible explanation for an event. Two things about hypothesis: it has to be falsifiable, meaning you can say, if this hypothesis is wrong, how do I know? Well, if this is wrong, it won't make any difference. If it wasn't the light bulb and I replace it, of course I still don't have light. And this will be highlighted. I probably should be bold, forgot. This is the most important thing. It has to be testable. I mean, when I came in the apartment and the light did not come on, I could have said, I think little green men from Mars are living in my lamp. That's why the light does not come on. Is that scientific? No. Not because it's crazy, but because it's not testable. How do you test for little green men from Mars in your lamp? There's no such a test. Okay? So in science, you have to come up always with an explanation that you can test, because that's how you know if you're right or wrong. If it's not testable, it's not scientific. So how do we come up with a test? This is deductive reasoning. It's like, if this, then. So these are scientists saying, if organisms are composed of cells, we know they are, but let's assume that you're thinking that, then if I examine the organism, I should see the cells. Okay? Some people say, well, he made a prediction. Yes, but when you're looking at examples, especially in an exam, the if-then argument helps you see if your hypothesis is reasonable. If you cannot say if this, then that, you need to reward your hypothesis. So to test the hypothesis, we do experiments. And in a good experiment, you try to keep all the conditions constant except one variable. What is a variable? The part of the experiment that can vary or change during an experiment. You only try to change one at a time, so you know what's causing whatever you're observing. I used to live near Clemson, moved to Greenwood. When I lived near Clemson, I had beautiful orchids. They just loved that apartment. Moved to Greenwood, all my orchids stopped blooming. Well, if I start thinking, what could be causing it? Well, Greenwood is warmer than Clemson. Greenwood is more humid. My apartment now has less light. If I start testing all the different possibilities, I'm going to get a headache. But if you choose one variable and you keep everything as constant, like maybe it's the food. Well, I'm not going to change anything, but I'm going to give them different amounts of orchid food. Then I can determine whether the food was the reason. Oh, it didn't work. Okay, I'm going to test light. I'm going to put some of my orchids next to this window. The other ones are going to be farther away from the window. So you change one variable at a time. Okay? There's two types of variables. The independent variable is what you're studying. In my example, I was looking at the blooming. So you could say that the independent variable was whatever I was changing to try to determine what was affecting the blooming. It could have been the light, it could have been the nutrients, it could have been the humidity. The dependent variable is called that because the number depends on the independent variable. You change the independent variable, and the dependent variable changes with it. It's the one that you measure. In my example, it will be the number of blooms. So I'll change the independent variables, change the nutrients, and look at the blooms. No, the nutrients didn't have anything to do with it. Okay, then I change the light. Oh, the orchids that are closer to bright indirect sunlight will gain a lot of blooms, the other ones didn't. So the dependent variable is what you measure, and it changes with the independent variable, that's the one that you change. Whenever you're doing control studies, you have to have two groups. You have a control group that receives no treatment, an experimental group that receives a treatment, because sometimes there are factors you don't think about that may affect that. So the control group will let you know if there's something else that is having an effect. And that's very important, especially if you are in medicine and you're testing a new drug in people, because psychosomatic effects will drive you crazy. Let me give you an example. My father-in-law, when I first got married, he told me one of the first things, that sometimes he couldn't breathe, and he had that spray. When he couldn't breathe, he sprayed his nose. Oh, that's interesting. Then the story started getting really fantastic. I remember going to visit him, and he told me, "You won't believe what happened this morning. I was in the kitchen, and I couldn't breathe. And I'm looking for my spray, and I realized it's in the bedroom." He claimed that he crawled through the kitchen, through all the length of the hallway, into the bedroom. He's about to pass out because he's not breathing, remember? And the bottle of medicine was on top of the bedside table. He took the wallet of his back pocket, threw it, hit the bottle fell on the ground, grabbed it, and he finally sprayed his nose. When he was about to die, he sprayed his nose and he's fine. And I remember thinking that, what? First, I think he's exaggerating, but what is in that drug? But he was getting it from a local drugstore, and when I look at the bottle, all said, spray twice his nostril as needed. It didn't tell you the ingredients. Well, time passed. I quit thinking about it until one day my father-in-law calls me very mad. "Doctor, what does saline mean?" And without thinking what he was asking, I told him that's nothing more than salt in water. And you can't imagine the profanity. I hung up the phone, Calm down, Papa, I'm going to see what's wrong. I drove over to his house. He was still furious. Ended up, CVS had bought the little local drugstore. CVS followed the rules, so they put the ingredients on his magic medicine. And it said saline. So when he found out that for years he had been spraying salt water in his nose, and that he had been telling everybody how that great medicine had been saving his life, he was so mad. But that's why you need a control group, because your brain will make you believe that something is actually working for you. That's called the placebo effect. Lots of people, the doctor figures you don't really need anything, and they give someone a sugar pill. But because they're getting a quote-unquote medicine, they feel better. Now, in experiments, especially, like say, when you're talking about medicines and people, the ideal thing is having a double-blind study where the person giving the pill doesn't know if it's a placebo or the real drug. The patient doesn't know, so hopefully nobody can put in their personal opinion. It's going to be as accurate as possible. So you do your experiment and you have to analyze the data, the results. Now, the results have to be something that's either observable or measurable. It has to be objective. It cannot be my opinion. I think that looks good. I think that's so. When you have mathematical data, you usually put them in the form of a table or a graph. So it's very, very easy to look at the results and see if there's any trend in there. You use statistics because statistics rule out results that are due just to chance. Sometimes it happens. But all of a sudden, when you do statistics, you realize, oh, the results for this particular experiment, they don't make any sense. I think I'm going to repeat that one. I think something happened in there. My professor, when I was working my PhD, used to say statistics is like a bikini. You cover what you don't want people to see, and you show what you want people to see. And it's true. And some people abuse it too. Sometimes the data may suggest that there's a correlation between something, but that doesn't necessarily mean causation. You have to be a skeptic to be a scientist. Let's say that you get an upset stomach every day after you eat, and you drink tea with your meals. Okay, that's a correlation between upset stomach and the tea, but that doesn't mean the tea is causing it. Could be something else. Okay, so just because two things happen at the same time, it doesn't necessarily mean that one causes the other. When you have analyzed your data, you develop a conclusion. Basically, is your hypothesis supported or not? Was you right or wrong? And keep in mind that all experiments and observations must be repeatable. That happens all the time in science. Someone publishes a paper, somebody else tries to replicate. No, it doesn't work. Where did you get your data from? Hopefully, that can be prevented with scientific journals where you have reviewers looking at that. But you come up with a conclusion. And first, you know if you're right or wrong. If you're right, not only you're adding more information, but your conclusion may give you another question. For instance, the work I did, I was studying a virus that causes breast cancer in mice, and it appeared in the milk. It was passed from the mother to the pups through the milk. So the first thing was to see that the virus was in the milk. Is it at all times during pregnancy? No, we did a time course looking at the virus, and it appeared at a certain point in pregnancy, and then it started going up. Well, that happens to be the time when progesterone kicks in a pregnancy. Just because progesterone is increasing doesn't automatically mean progesterone is inducing the virus. But we did studies in vitro, and we proved that progesterone stimulates the transcription of the virus. Okay? And of course, if your results are wrong, then, well, you need to come up with another hypothesis. You need to know that you're wrong so you can figure what another possible explanation would be. Finally, your scientific studies tend to be published in a scientific journal. You don't have editors that look at your English, but you have people who look at, is the science correct? Can the results be replicated? Is this really new? So that ensures reliability. Is very different from what the general public gets, that you just get secondary sources that may come from a good source, but they're more interested in selling. These scientific journals are written by scientists, reviewed by scientists, read by scientists, and allows you to share scientific findings which could lead to future discoveries. Finally, I want to give you an example of a control study. Most stomach ulcers are caused by a bacteria, Helicobacter pylori. Yes, people say, but nerves died. Yes, the stomach, you will study, protects itself very, very well. But if something goes wrong because you produce too much acid, for instance, because you are a nervous wreck and you produce too much acid, you weaken that protection, and then the bacteria has a chance to attack the wall of your stomach. So many times, ulcers can be treated with antibiotics. So my hypothesis is, okay, we have antibiotic A that we're using, it seems to work fine, but maybe this other antibiotic that we just developed is better. If we are going to sell it, if we are going to advertise, we need to prove. So what we do is and obviously not one experiment, but multiple experiments, have large groups of people and have 3 experimental groups. One group is going to receive the placebo, and they don't know it. Okay, that's important. That's a control group. Another group is going to receive antibiotic A. Another group is going to receive antibiotic B, and we're going to have the antibiotic for a couple of weeks, and then we'll see. The idea is nobody knows who they're taking, so they cannot just say, oh, I'm feeling better, because I know I'm taking the medicine. Nobody knows what they're getting. That's the problem if you get into an experiment like this. You may not get a drug, okay? I had cancer 10 years ago. There was no chemo for my particular type of cancer, and the doctor said, we could put you into some experimental studies. Well, I really wasn't interested. I understand that that's how they develop new chemos and all that, but if I'm not going to take the drug, or I don't know if the drug works or something like that, I just have enough on my plate right now. No, thank you. Okay? But we have 3 groups of people. Like I said, some people get a sugar pill, some get 1 antibiotic, some take the antibiotic with a couple of weeks, and then, and to make sure this is very objective, not just the opinion of the people, they did an endoscopy where they put a camera into the stomach to see if there's an improvement. 10% of the people who took the sugar pill had less. Well, these other factors, the stomach self-repairs. So that's not surprising. Group 1 that took antibiotic A, 60% improved. The group 2, 80% improved. So obviously antibiotic B works better than A. And you can advertise saying in control studies, antibiotic B has proven to be more effective than antibiotic A. So high percentage treated, the hypothesis has been supported. So if you want to work on me on a one-on-one basis, if you want to take advantage of any worksheets, charts, anything that I may have made for my classes, if you want to study for an exam, there's a link to my Wishand Turing profile in the video description. You can make an appointment, and I'll be glad to work with you.